Hello and greetings from FORTE Ilmenau. Today I am going to present you the latest achievements of the Rescue Working Package 4 team in experimental evaluation of the TOIS Scenario 1. Since the last report presented to you, our team managed to come over from pure software simulations to practical evaluations of the rescue concept. The results I am going to show you in a moment. And for now, please follow me to the lab. We are at the FORTE facility, and today I am going to present 3 test methods regarding TOIS Scenario 1. We will start with a connected test in a fully controlled environment. Then we will come over to over-the-air transmission in anechoic chamber. Finally, I will introduce you the test case on indoor radio transmission. So let us start with the connected tests, which we are going to focus at during the major part of this video. The hardware equipment we are going to use are various computer platforms for running rescue code. These are regular desktops running Linux and GNU Radio, as well as compact Intel NUC platforms, which we are going to use later during our rear-field experiments. Computers are connected with Ethernet cables to software-defined radio devices called USRP, which serve as the radio front-end at each node in TS1 scenario. Here we have again a mixed setup consisting from 2 latest generation devices X300 and 1 older device N210. The operating frequencies are 2.45 GHz. In the connected test, the RF ports of the USRP devices are connected to over-the-air channel emulator. The auto channel emulator allows us to set up channel parameters and model each radio link individually. Furthermore, we can perfectly reproduce channel conditions between individual runs. Now let's take a precise look at the TOIS Scenario 1. We have got 3 communicating nodes. Each node consists of 2 major blocks: a computer running rescue code and an USRP device used for radio communications between the nodes. Each USRP device has got 2 antennas attached, one for transmission and one for reception. The communicating nodes are the source, where the data flow is generated and sent towards the destination, the relay, which in the rescue LOFT mode forwards even corrupted packages at destination, and the destination node, which does the main job applying rescue algorithms. The nodes communicate with each other over radio channels with different parameters. The channel between the source and the destination nodes is very noisy, which introduces a lot of errors into the packet transmission. The channel between the source and the relay is better, but still noisy. And the radio channel between the relay and destination nodes has very high SNR. In the connected tests, these channels are emulated, and the RF ports of the communicating nodes are attached to the channel emulator directly with cables. For convenience, we will use one additional laptop for centralized monitoring upon communications log at all the 3 nodes simultaneously. Now let us look at several test cases applying connected test method to TOIS Scenario 1 evaluation. In the most simple case, there are only 2 nodes communicating, the source and the destination. They communicate over a very lossy channel with low signal-to-noise ratio. The source sends each packet only once, not taking into account whether the packet was received successfully at the destination or not. In the destination log, we see one message for each physical layer packet, which header, but not necessarily the payload, has been received without errors. For these packets, we know the packet ID. Frame successful rate equals 0 means that for every received packet, the payload was corrupted, and the MAC layer was unable to decode such a packet further. For the second test case, we introduce an additional route for the packets, the one over the relay. At the relay, we do not allow lossy forwarding, which means if a packet gets corrupted on the way from the source to the relay, it will be discarded by the relay. Now in the destination log, you can notice that the packets arrive from two nodes, the source node and the relay node. You can also notice that some packets coming from the relay are successfully decoded at the MAC layer. In the test case 3, we introduced the rescue functionality, namely lossy forwarding at the relay and joint decoding at the destination node. In this case, even corrupted packets arriving from the source will be forwarded by the relay to the destination. At the destination, two corrupted packets with the same ID can be jointly decoded. This increases the frame successful rate at the destination node. In the fourth test case, we add one retransmission at the source while keeping all the other parameters the same as in the previous test case. Notice in the destination log, now we are able to receive almost all the packets from the source. Unfortunately, still not all the packets can be successfully decoded by the MAC layer. As the next step after performing connected tests with perfectly controlled channel parameters, we can come over to real radio transmission, which is at first performed in the anechoic chamber with no interference from other communication systems. In the chamber, you now see two magnetic mounted antennas of the destination node. The signals from the source and the relay can be fed to any individual antenna in the antenna ring. Finally, let's take a brief look at the third test case, the indoor radio transmission for toy scenario 1. In this case, each node consists of an USRP, a computational module based upon Intel NUC, and two magnetic mounted antennas, one for the transmitter and one for the receiver. This setup now is very similar to the setups we planned for the real field experiments with car-to-car communications later this year. Of course, additionally, we will need some more equipment, such as GPS loggers to track the car positions, cameras to visually record the environmental conditions, such as traffic or line of sight scenario, and some equipment to provide power supply for the nodes in the cars. At this point, I thank you for your attention, and I also appreciate the help of my colleagues from TU Ilmenau in creating the setup and assistance in conducting experiments. Also many thanks to the colleagues in the partner institutions who supported us in various technical issues.